Okay, let's take a look at today's lesson. We're going to look at average value of a function. And so how I want to start out with is talking to you about average rate of change. We have to talk about these at the same time because we've got to compare and contrast them. When the problem that you're going to be working says average, it could mean either one, regardless of how it's written. So we need to be able to tell them apart. Okay, let's tell them apart. So let's talk about first average rate of change. We learned about the average rate of change, right? Average rate of change we found by taking the slope of the secant line. Remember that? That's average rate of change, slope of the secant line. And so when we learned the mean value theorem for derivatives, the mean value theorem told us what? It told us that the slope of the secant was going to be equal to the derivative, or the tangent, slope of the tangent, at least 1 point, right? And with all of that, we're dealing with rates, derivatives. With me? We're estimating, we're doing the average rate of change, which is slope of the secant. We're comparing it to a derivative. So let's get that in our head. That has to do with rates and derivatives. Average value of a function has to do with average y values. Average y values of the function, not the derivative, of the position or whatever function we're dealing with. And so let's look at the formula for average value. So the definition for average value on the interval a to b, they like to signify it as FAVE, F average, that's a function average, not the derivative average, the function average, is 1 over b minus a, integral of a to b of f of x dx. Okay, so that is a formula to find the average y value of the function. And this is a picture of what that would look like. Here's the function g of x. It's what it looks like. This is our average value here in the little pink dotted line. And if we were to reconfigure this area, it would, in theory, make a rectangle. That's what they're trying to show. It's the average y value. So they're trying to show us that if we took all of these y values and added them up and divided by how many y values there were, which you can imagine that's really not something we can do, right? Because there's an infinite number of both. That's what this formula does for us. This formula does that. It adds up all the different y values and it divides by how many y values there are. That's the beauty of, well, one of the beauties of calculus. So that's the concept that we're going to be working with. Now let's look at the mean value theorem for integrals. We just talked about the mean value theorems for derivatives, right? It was the slope of the secant is equal to the slope of the tangent line at least one place, right? All right, so let's look at what we're for the integrals. What this is telling us is the average y value is going to be equal to at least one y value at whatever c is the x value, one time, at least one time. Okay, and I know the words don't say that, but that's what it's saying. It's saying my f average, which is this formula right here, is going to equal my actual function value at some x value. Okay, so it's comparing the average y value. It's saying, look, here, how many times does the function attain the average y value? It attains it 1, 2, 3 times, right? That's what this is saying, that you will attain it. I mean, it could be multiple times, but at least one time. Does that make sense? So I hope we will be talking about the difference between average rate of change and average value all throughout the rest of the year. I just need to be sure we're clear when you first hear average value, how it is different than average rate of change. Okay? All right. So that is our new concept, average value. And we're going to work some problems to demonstrate how that works. Any questions in particular so far? Okay. All right, so let's take a look at this problem. We're given f of x equals 1 plus x squared, and we're on an interval, a closed interval, -1 to 2. Find the average value of f on the given interval. Now, let's go through that. Average value of the function means average y value. It's being very specific with us. Average value of f. We have f. We're using f to find the average value, so that means we're using our integral 1 over b minus a. That would be a, and that would be b. So 1 over 2 minus a minus 1. And my function is 1 plus x squared. Okay, so that's going to give me my average y value when I work through that. All right, so let's take our we're from -1 to 2. All right, so let's take our antiderivative. So that's going to be 1/3 times. That's from my first part of my formula. Let's see, x plus 1/3 x cubed, evaluated from -1 to 2. So 1/3 times. So let's drop the 2 in. So 2 plus 2 cubed is 8. So 8/3 minus, with a bracket. Let's drop the -1 in. And -1 cubed is -1. So -1/3. Okay, so I do my exciting arithmetic, and I end up with 2. 2 is the average y value on that interval. Okay, on that interval, average y value on the interval. So now they're asking us to find c. I mean, we're familiar with that with the mean value theorem, right? We found c. This is a different concept of c. C is where the x value, where the function's y value is equal to the average value. Okay, so we're going to set our average, which is a 2, equal to our function up here. So we get 2 equals 1 plus x squared. So x squared equals 1, x equals plus or minus 1. Now, hopefully we remember from our mean value theorem days that we have to check the interval. Okay. What do we remember about the endpoints of the interval? They don't count, right? So they don't count on this one either. The mean value theorems are the same. They don't count. Okay, can't use it. So my c value here is simply going to be 1. Okay? So now it wants us to sketch the function and the rectangle whose area is the same as the area of the graph under the function. So we're like on that other slide, how we were, we saw the area under the function plus the one with the rectangle. That's what they're wanting us to do. So to graph the function, this is a parent parabola shifted up 1. So it looks like that. We want our interval from -1 to 2. And so we're told that our average y value is 2. So we draw our little box here. That's the area. And according to our drawing, hopefully we can see that right there is where our function attains the average y value on the interval. Okay, we okay with that? Yeah, I know, that's troubling, isn't it? It doesn't count because it's the end point. It's probably very sad about that too. But it doesn't count. Okay. So the last problem, we're going to look at a graph that's already been drawn. So suppose that during a typical winter day in Minneapolis, the temperature in degrees Celsius, x hours after midnight, is shown in the figure to the right. Use a midpoint Riemann sum. So that's rectangles. We're going to be finding area of rectangles and adding them up. Midpoint Riemann sum with 4 equal subintervals to approximate the average temperature over this time period, 4 to 8. So now let's be sure it's x hours after midnight. So 4 p.m. would be 4 hours after midnight, right? Or excuse me, 4 a.m. For 8 p.m., 8 p.m. would be how many hours after midnight? 20. 20 hours after midnight. Okay, so we need to be sure to translate into how they have set the variable. All right, so we want the average temperature. So we're going to do 1 over b minus a, and this is called, well, we'll call it f of x dx. Okay, so 1 over 16 times. Now to get this part, we're going from 4 to 20. We're going to have to go over here and get that area over here. So from 4 to 20, and we need to do 4 equal subintervals. So it looks like there's our 4 rectangles right there. Okay, so they're all, let's see, they're 4 apart. The width is 4. Now it's a midpoint Riemann sum, so that I'm not going to be finding f of 4 or f of 8. I'm going to be finding the midpoint, which would be f of 6. So f of 6 plus f of 10 plus f of 14 plus f of 18. So 4 times, and it's the kind that y'all don't like where we have to estimate. And so that's fine, let's just estimate. So f of 6 is down here. Let's see, I estimated that at -5 plus f of 10 is right here, and I estimated that at 1, and f of 14 is right here, and I estimated that at 2, and then f of 18 is right here, and I estimated that at -1. So I add all that together, multiply by 4, I get -12. Alright, so that's our integral. So that takes the place of this little guy right here. So -12. 1/16 times -12 gives me -3/4 degrees Celsius. So that's my average temperature over that time period. Now they want us to use that to estimate the time when the average temperature occurred. So one of the most straightforward ways to do it would be just simply draw a horizontal line at -3/4 and try to estimate what those x values are. Alright, so this is in a scale of 2, so -3/4 would probably be about up here. Of course my line is off, but I think we get the idea. So here and here, which is around, I estimated it at 9. That's around 9 and around 17. Again, that's an estimate. And that is hours after midnight. Okay, how are we on average value? We okay? Yes? Yeah, sure. Instead of saying after midnight, you can actually calculate the time. It'll be fine. Any other questions? Alrighty.